Thanks for having me. Appreciate the chance to come out here and talk. I'm a research geographer again at USGS. I moved up here about 5 years ago now. I've been with the survey for, I'll be celebrating 20 years here in a couple of weeks. I got started at the survey as a geographer. Remote sensing was my background. Spent about 10 years on various projects that were really geared around characterizing land change in the US, both cover use, disturbance. It's part of some really big, exciting projects with Tom Loveland's kind of served as a mentor of mine. We kind of got to a point where we had done a lot of this kind of historical mapping, characterization, and we began to move into projection. And I got started on a project I'll talk a little bit about, but we really focused on downscaling land use scenarios, and that was to feed a big carbon assessment. And then, I don't know, about 5 years ago, I somehow got roped into the world of ecosystem carbon balance. I'm not sure that's been a great thing. It's been exciting, it's challenged me, but nonetheless, I'm in it now. And I couldn't have picked a crazier place to do it than in California. So anyways, I'm going to talk about some research that we just had published 2 weeks ago. It's actually in press, but really what I kind of focused this talk on was kind of our modeling approach, where we're doing carbon, but we also, the focus of the research really is on land change science. Just a few acknowledgements. I've got a team. Those folks are all down in Menlo Park, and they've been integral to a lot of various elements of this. I also have a real close working relationship with a Canadian firm, Apex Resource Management Solutions. They've been outstanding, actually make the software that we use. Some folks at Nature Conservancy California, Leroy Westerling at UC Merced, David Stoms at the California Energy Commission. So without those guys, none of this work would have happened. As Dan mentioned, there's kind of two big projects that I've been a part of lately. These are ongoing. One is, I don't want to get into the whole government funding thing, but basically we've got two programs. One is called Land Resources R&D. Used to be Climate and Land Use Change, but we don't say those words as much anymore. Land Resources R&D, and this is really geared on developing land use scenarios, developing different methods of making various projections. And then there's another program called what we effectively just call Land Carbon, which was established back in 2007 by the Energy Independence Security Act. A specific section in there asks the Department of Interior to conduct periodic assessments. And it's not just for terrestrial ecosystems, there's a whole geologic component to that as well. In addition to kind of doing the assessment activity, the legislation actually requires us to try to understand and quantify various controlling processes and understand or try to evaluate the effectiveness of various mitigation actions. We'll talk a little bit about where we are, but the first assessment we completed in a series of regional reports. This was for all 50 states. We published a methodology, and then these regional reports, 3 for CONUS, and then a separate assessment for Alaska and another one for Hawaii. It was a really intensive effort, took several years to complete, very much oriented around process-based kind of biogeochemical models. We included aquatic carbon fluxes as well. There was a separate fire spread model that was done. We did N2O and CH4, and it was a pretty high resolution for national assessment. We did this on an annual time step at 250 meter resolution for the country. And there's not a lot out there that's been done at that level. So it really was an exciting kind of first step, but it also came with a lot of negatives. Kind of stepping back afterwards and evaluating what was done. The treatment of uncertainty was very much lacking. Again, these big process-based models required a ton of compute time, a lot of parameterization, and effectively getting at uncertainties was challenging. There was very little in the way of actual model integration, linking, no coupling, specifically between the biogeochemical side, the land use side, and fire. It was based on the old CMIT-3 or SEFS Scenario framework, if you're familiar with it. So these are the A1B, A2, B1 global change scenarios. And while they're great, they come with a nice coherent set of narrative storylines. They're, so to speak, outdated now. We've got newer sets of scenarios and newer climate projections that we need to deal with. And again, the kind of bigness of this assessment made substituting in new scenarios pretty difficult. Again, very complex, a lot of compute requirements, and it's kind of suffering from that black box nature, right? It's a big set of models, integrated models, and they're very hard to explain to people. They certainly can't be handed off and run by somebody else. And so we kind of wanted to move away from this, identifying these limitations and hopefully improving them. So now we're talking about moving towards more of what we call a sustained assessment, something that can be updated annually as new data are available, new climate projections are made. We also want to be able to couple models. We think that's really important. There's feedbacks between land use and obviously fire, certainly carbon dynamics that need to be represented. We have to get at uncertainty, and I'm going to show an example of how we've done that for at least one particular input parameter. Obviously increasing transparency. We wanted to focus on relying on real data to drive the models as much as possible. And a lot of times that comes back to remote sensing. We started to build in some mitigation adaptation capability. Again, I talked about remote sensing, and we also recognize that in this day and age, this stuff has to be open, reproducible, available to the public in more than just a complex set of maps. The whole code base needs to be available. So we're really trying to push it in that direction. Okay, so how are we getting there? I've been working with Apex for some time now. If you're familiar, some of this work, it goes back a long way, at least in the federal government. Apex develops state transition simulation modeling software, and they go way back to something called VDDT. And these were very old, they were developed a long time ago, they're these old state transition models that showed forest succession, vegetation succession. They were done across the US. I think there were a couple of thousand of these VDDT models. They're actually kind of the backbone of a program called Landfire. Landfire is something the US government sustains, a mapping effort and a modeling effort, and characterizing vegetation in the US and fire risk and stuff like that. So there's a rich history working with these state transition models. We've done a lot of work to improve the software. We've gone to this package-based approach, and I'm going to talk specifically about state transition simulation package and a stock flow package. There's also a population dynamics one that I haven't been working with. But this has been a collaborative effort by numerous governments and institutions. So what is SynchroSim? SynchroSim, it's got a Windows UI. You can run this on your laptop if you like. It's very robust software, very stable. There are Unix and command line tools in a Unix version if you're wanting to get into some of the high performance computing stuff, which we do. There's also an R package, so everything can be done right out of R. We're also in the process of finishing the Python one. The state transition model and the stock flow model are fully coupled, so they're feeding inputs back and forth to one another at whatever kind of time step or resolution you want. The SDSM and stock flow are open source. They're really well documented. These are the two publications that we put out. Colin was the lead author. One describing the SDSM and one describing how you integrate stocks and flows into a state transition simulation model, both published in MEE. Really provide all the background. So what I've done is I've taken this framework, and it really is a framework. Okay, there's no set number of classes or anything like that. You can take the SynchroSim modeling framework and do a lot of different things with it. What I've done is developed what we call LUCAS, the Land Use and Carbon Simulator. This is, again, a general approach. Okay, so I'm focusing on land use, land cover change, but people often use this exact framework to parameterize vegetation succession post-disturbance. We've had applications where we focus purely on urbanization. So you have almost limitless flexibility under the hood of one of these things. It is fully coupled. What we did here with LUCAS was kind of a foundational model for California's recent climate change assessment. We were able to link it up with an exogenous fire model developed by Leroy Westfield and Merced, and we developed a drought-induced mortality, forest mortality model. Since 2015, we've had about 20 scientific publications and data releases that have been based on LUCAS. Again, very much a collaborative effort. And I'll talk about quickly a couple of applications that are a little different from where I'll spend the rest of the time. This one grew out of another guy on my team, Nate Wood, who's very much into hazard, risk, and exposure. And we just got the idea that, when you look at tsunami hazards in the Pacific Northwest, for example, you're often talking about a hazard that might not occur for 100 years. It's well recognized. But what never follows there is, well, what does the landscape look like in 100 years? We always apply the landscape today. Well, that could look very different depending on where you were. And so we came up with a very simple approach. We built up a model. We just looked at urbanization here. And we developed an empirical projection of urbanization. We collected historical data from remote sensing, National Land Cover Database here, and projected out at 1 hectare resolution for 17 counties or so in kind of coastal Oregon, Washington, Northern California. And then we looked at how that exposure to this hazard what it might look like 50 years from now. It was really a neat one, and we've got a lot of positive feedback from the disaster risk folks, and they want us to do a volcano lahar hazard one here for the state now. We also, this really kind of underpins a lot of the work we've done, but when we started this, California entered this period of really exceptional drought. And as we were building the models, this water use thing is staring us right in the face. And so we also had a model where we parameterized, we developed these basic land use projections, kind of what we call a business as usual, or a continuation of historical trends. But then we also just tracked, very much in a lookup approach, how water use would change. If we assumed no technological innovation or no new efficiencies, just what's going on today, just purely due to changes in land use, what would happen to the demand for water. And in California, the pattern very much is rapid urbanization, often at the expense of agricultural lands, but you also have a change going on between rangelands and agriculture. So rangelands are often being eaten away by the expansion of almonds and walnuts and vineyards, which are replacing traditional field crops down the valley floor, which are being eaten up by urbanization. So you've got this exchange of land uses, and these have resulted in about 4 or 5% increase, projected increase in water use. And while that doesn't sound like a lot, at this time, California enacted a mandatory 25% cut in its residential water use. And that 5% basically equals maintaining that 25% cut forever. And that would keep you at the same amount of water use going forward. Well, literally the day this was published in ERL, the governor pulled back the 25% cut. Literally that day. But it's another application of how you can use the model, and again, everything is tracked within this single sim framework of this model. And then we've got a few applications right now related to conservation biodiversity. One of my colleagues, Kristen Bird, has been doing a lot in California rangelands, specifically looking at how protecting rangelands can affect carbon balance in the state. They've had a lot of stakeholder-involved workshops and stuff. There's a data set that we published on this, and there's a lot of this material rolled up into the climate change assessment. And another one of my colleagues, Jason Kreitler, is we've taken this nationally, and he's looking at threats to protected areas resulting from changing land use into the future. I've mentioned the fourth climate change assessment. We really got pulled into this at the request of David Stoms, to the California Energy Commission, and what they wanted was a set of wildfire projections informed by land use. And most of the wildfire projections up until that date didn't have a changing land use base. And so that's what we did. We worked with Leroy and developed a set of these projections that he then took and ran his fire model. And then that data was then distributed out to a whole bunch of different people, including folks working on infrastructure, for example, transportation infrastructure, fuels infrastructure. The applications actually really started surprising me. Somebody approached me, I forgot to have a reference here, where they were looking at heat stress under various climate change scenarios, and kind of the duh thing hit me. Well, yeah, we should look at heat stress and exposure, but with a changing land base, right? It can't be based on today. As if we're looking at a hazard likely to occur 50, 60, 80, 100 years into the future. So several applications have grown out of this, and kind of specifically, the underpinning to this was published in Earth's Future, but it was this set of land change projections. And the way we tackled this was, it wasn't a downscaling effort, rather we kind of went the other way. We looked at, California's got a really rich history of, a rich database of remote sensing-based land use change products. It's called the California Farmland Mapping and Monitoring Program, and they actually hand digitize aerial photography every other year. So it's this really nice data set. And we compiled the whole history of that data set and then sampled from it. And we sampled from it in different ways. We looked at periods where, say, urbanization was low, urbanization was high, and we sampled from the whole range, we truncated certain years. And we did that also with ag expansion, ag contraction, and forest harvest. So we developed this historical data set, projected into the future. We call that a business as usual scenario, but then the state came in and gave us county-based population projections, and we used that to further modify our urbanization projections. So this was published, annual projections out to 2100, 1 kilometer resolution, and this really kind of became one of the main pieces for the work I'll talk about now. And so this was, how do we project carbon balance changes in California ecosystems? This is just published in Global Change Biology. We took this scenario-based approach. We have these 4 land change scenarios that kind of underpin everything, what we're just effectively calling BAU, high, medium, and low. And then we took 2 of the radiative forcing scenarios, so these are your RCPs, 4.5 and 8.5. And then we took 4 global climate models. And the 4 global climate models, these are the ones that were selected not by us, but by the state. There's actually 32 of these that are part of the LOCA downscaling effort. There's 32 of these. The state kind of went through a big analysis project. They came up with 10, and then they said you should do all 10, and if you can't do 10, you have to do 4. You can never pick 3 because everybody will pick the middle one, so you got to do 4. And so these are the 4 that they recommended. And then for every one of these combinations, so these 32 combinations, we ran a model, we ran 100 Monte Carlo realizations of the model. So this kind of becomes what we call this 32 futures paper. What we also did, and I just have to say that like this was an example of the peer review process just working really well. We got a great peer review on this paper, not that it was all complimentary, but that the reviewers really got into the paper, spent a lot of time with it, and came back and asked the obvious question that I kind of knew was hanging out there, but what about CO2? And how did you deal with it? And we were very clear in the paper that we did. We took the assumption that the uncertainties are so large that it was the more conservative approach to not include it in these base runs. They wanted us to rerun the models with a basic effect, and we kind of came to this, and we conducted the sensitivity analysis, which I think turned out really well. We've gotten a lot of real positive feedbacks from the reviewers, but from some other folks that I've talked to. So here we took the BAU land use along with our average climate model for both of the RCPs, and we ran 5 new assumptions around the CFE, this carbon fertilization effect. And for those, we ran 20 Monte Carlos of the model. And so I'll talk a little bit about the results of all that and what it means. First, just kind of general idea. I know these are hard to read, but they're kind of tough and ruthless. But generally, what I wanted to convey here was there's a lot of external data that come in. So radiative forcing scenarios. Those get fed into an integrated assessment model. Those produce greenhouse gas concentrations. That's this. This is all outside of what we do. Global climate models, downscaling, historical data, all produce this set of climate variables. And the big thing that we did was took these climate variables, temp and precip, and we used those to project changes in NPP. We used them to project changes in the turnover rate of dead organic material. And then we also used them both in these kind of exogenous models, these exogenously linked models, to project wildfire and drought-induced tree mortality. And so that's how climate really drives the various aspects of the model. And then up here, kind of the underpinning of our carbon model is something called IVIS. It's a dynamic global vegetation model developed by John Foley years ago. Pretty well-respected model. And so we derive kind of base flux rates out of IVIS and feed it in here, and then we modify those in space and time. And most of the modification of these is occurring based on climate data. There's a lot more here, but that's kind of the essence that I want to convey to you, that climate drives both carbon directly through changes in productivity and turnover, but it also is driving state changes, specifically around disturbances. It is not driving land use, right? So climate is not affecting the rate of urbanization at all. So now if we drill into one of these dudes, the Lucas stock flow and the STSM, and our STSM model is quite simple. So the green boxes are what we call states, or land use and land cover classes. I'm using land use and land cover for those of you that are in that world. You might cringe at it. Trust me, I know, I know the differences. But actually in the model, we do have a bit of a hybrid. Forest is treated more as the traditional use class that the Forest Service might define, where some of these others are based more on cover. But these are the basic classes that we have, and then the boxes in here are the transitions that we invoke. Okay? And so mostly, we're talking here about demand for land uses, which can be the expansion of agriculture or urbanization. Once urbanized in the model, you're there forever. We're not turning cities back into forests right now. Most of that just because of the nature of the courses in the model. We have this perennial and annual breakdown in our ag classes, again, mostly to get at the carbon differences in the turnover of orchards in California. It's actually quite important. And then you can have this contraction of ag, and then we go back into one of these kind of what we call a natural vegetated state here. And then we've got fire, three different severities, and drought-induced mortality, also severities. But you'll notice that these don't result in a state change. It does result in an age change, or can result in an age change. But we're not taking forests, burning it, and calling it grassland. And that keeps us consistent with the way Forest Service often reports changes in forest area. This is what the stock flow model looks like. So it's not an overly complicated carbon model. We've got some basic pools, a live pool, 2 dead pools, a standing and a down, a litter pool and a soil pool. And then we track the fluxes of carbon, obviously through those basic pools, but also when land is harvested, either forest or agriculture is harvested, we have a set of product pools. We also have this leaching flux. So this would be the lateral transfer of carbon into aquatic systems. And right now, these, in this particular approach, these were bathtubs. So when the carbon went in, we just collected it and made sure we still had a mass balance in the model. There's obviously a lot of work, right, that would come with arrows out of here and out of here. Whole set of research that we're actually beginning to build on. Dave Butman, who's here, has done a ton of work down here, which we want to bring back. Dave was instrumental in our first land carbon assessment. So again, a pretty simple, this is kind of based on, for the most part, IPCC, tier 1 methodology. This is what the model actually looks like, the input, the basic input parameters. So the model requires a set of initial conditions. So this is, a land cover map, or our state class map for California, red being the urban area, the Central Valley right here, Sierra Nevada over here. Age is another really important input into a model like this. Luckily, there's a great product that Forest Service developed. They did a gradient nearest neighbor approach to estimating forest age from FIA plots, but it's only for Oregon, Washington, California, 30-meter resolution. When we start talking about scaling, this is tough. We need this product, and it's actually a really big source of uncertainty. We also stratify the model in 3 ways here, and we've been using ecological regions for a long time, working on land use change. But we also recognize the need to have some kind of socioeconomic structure to the model. And so in this case, we're using counties, but these could be anything you want them to be. You could have states and counties. You could have different ecoregion hierarchies. The model doesn't care, but you just have to parameterize it with whatever you're putting in here. What we basically do here to differentiate things is for a natural process, quote unquote natural process, like wildfire, the parameters will often be done at ecoregion, using an ecoregion framework. Whereas things like urbanization are much more, much better described with counties, right? There's various policies put in place at, say, county scales or combinations of counties or combinations of administrative districts within a county that make a structure like this better for some land use transition. So it depends on the parameter, but we have lots of different options here to build on the model. Okay, so we ran the model again, 32 futures, 100 Monte Carlos of each, and this is what the land use projections look like. This is land use change. And again, we've got these basic categories: urbanization, expansion of ag, contraction of ag, and then what we're just effectively calling management. Management being forest clear cutting, selection harvest, and then orchard removal, which is down here. And just quickly about orchard removal, this is the process. In California, almonds are, turned over roughly about 25-year period. But if you've ever seen what happens when they remove one of these orchards, it's quite dramatic. They oftentimes pull the whole root ball out, and so a couple of meters of soil are actually turned over at that point. And that's obviously got important consequences for carbon flux, the oxidation of the carbon in the soils, and the complete removal of all the biomass that's on the site. And so this became kind of an important one. It's just a big thing in California right now. But the big story in California, right, is not so much around forests. It's about demand for land use in rangelands and shrublands. So kind of in the more northern part of the state, it's demand for herbaceous grasslands, for both urbanization and ag expansion. Down in the southern California area, it's more of your coastal shrubs that are being affected. But this figure just shows the contribution of the source classes to urbanization, for example. Show the next slide here. So this is state class area, or this is now the composition of land based on those transitions. And you can really see the differences here in development. So the gray here is what what we refer to as that business as usual scenario. So just taking the last 20 years and saying the future looks like that and keeping it going forward. And then the colored ones are the high, medium, and low population scenarios. And the interesting finding there, and we talked about this in New York's future paper, is that even under a high population scenario, and this was a scenario that the state, we really pushed them to develop. They really like this one. And all the demographic folks will tell you, well, absolutely this will happen, no problem, right? But doing scenarios, right, you always want to kind of push the edges. That's the point of scenarios. Well, even with this one, which is I think 65 million people by 2100, if you just preserve the last 25 years of land use change rates, we exceed that population projection. So I mean, it's kind of an important thing to turn around and think about that you know, sustaining this amount could have a bigger impact. And that the rates that we've seen over this recent period are, for the most part, pretty exceptionally high. The effect on natural ecosystems is pretty apparent. Under virtually all the scenarios, natural ecosystems are declining. So that's obviously got an impact on carbon balance. It's also affecting agriculture here. Under only the high land use scenario did we actually increase the amount of agricultural area. And just remember that we're modeling the gross changes here. So we're not just modeling a net outcome that we want. But we're throwing in rates that have ag increasing and declining from 58 different counties. And the outcome of that is the net change. Okay, so a lot of these projections have started with just net. But if you only look at the net change, right, you could miss a lot of conversion that's on the landscape and a lot of conversion that affects carbon. These are the projections of fire and drought-induced tree mortality. So fire on the top. We have our different climate models, RCP 4.5 and RCP 8.5. Same thing with drought-induced tree mortality here. And then the colors are the different severities. As you can see, you know, there's tons of variability. Under RCP 8.5, you do have a general increasing trend going on here. That signal's a little bit more mixed in RCP 4.5. This is kind of an interesting spike that I'll talk about under the Hadley model. This is our hot, dry future. Kind of, I don't want to say worst of the worst, but it's a pretty bleak future in California in terms of temperature and precip. But we get this really big sustained period of pretty intensive drought. So what does this all mean for carbon? So over this historic period, it's a random model from 2001 to 2015. We have an estimate of 4.8 petagrams of carbon stored in California ecosystems. I should just quickly clarify, we didn't model wetland carbon in this model. So carbon, say, transferred from agriculture to wetland. We didn't lose the carbon, but we just locked it up in a vault. Same thing with urban. We don't continue to model the fate of carbon in, say, an urban forest. So this 4.8 petagrams of carbon storage in 2001 is roughly broken down between live soil and dead organic material like that. And by 2015, it declined by about 188 million metric tons. Huge amount of variability from year to year. We range from a net source of 90 million metric tons to a net sink of 60. But there's really two periods that emerged. The first 10 years, you know, California was kind of carbon neutral-ish, a decline of about 2.5 petagrams a year. But look what happens when we enter this prolonged drought period. Really, really big carbon source, 40 million metric tons a year. And most of that was driven by declines in productivity. But there certainly is an effect of fire, you see. There's also an effect, although it's mostly lagged, with drought-induced tree mortality, right? When a tree dies, we don't lose that carbon from the ecosystem. It's still there, but there are certainly changes in the way that cell is regrowing and its productivity. So you're getting a lag effect there. You're also getting a lag effect in the turnover of that dead carbon. And so I thought it was interesting. What do those numbers mean? Like, what is the magnitude how do they compare to other things in the state? So we pulled the CO2 emissions from all the other inventory sectors in California. So, electricity generation, imported, in-state, transportation, industrial, commercial, etc. And so you kind of get a sense for where the ecosystems lie in this whole story here. And over the whole historic period, the losses from ecosystems represented about 10–11% of all carbon emissions in California. But during the last 3 years, it was about 35%. And so this period of exceptional drought, again, California ecosystems being a really big source.
When you say ecosystem sink there, it's not always a sink.
Not always a sink, yeah, that's correct. So the positive values up here. Anytime that green is NT is a positive, it's a source, yeah. You also get a sense, right, for wood products, this piece down here. And just keep in mind, right, that was a bathtub in our model. So the carbon got put in it, and we just assumed it was there forever for the purposes of the model. We know that's not the case. We know that's decomposing as well. Over time. And then you're seeing the effects of fire. It's certainly important. It can be really important in certain years. What's kind of neat, right, is the trend line of California inventory emissions has been declining. But once you include the ecosystems, you're getting a positive increase. Now that might stop. Maybe California enters a real favorable climate period. Maybe not. We compared it's really difficult to validate a model like this, and just upfront about it. We've done pretty extensive validation on the land change side, but on the carbon side, the boundary conditions of the model can really make it challenging. But we were able to validate some specific fluxes, in this case fire emissions. This is from the California Air Resources Board, Klaus Scott, and they actually use a model called FOFEM, and they take in burn perimeters and then actually estimate carbon emissions from fire. Now, granted, we're using the same perimeters because we all rely on the same burn perimeter data set, but his fuels, or the fuels used in FOFEM, the way fire spreads, completely different. So this was at least encouraging. We're roughly in the right ballpark here in terms of fire emissions. And then this is NPP. Not as in sync, so we compared our estimates of NPP to that from MODIS. But you have to keep in mind, this comes up in peer review all the time, MODIS NPP is not an observational data set. It is a modeled product as well, and it relies on MODIS land cover to kind of underpin that. So there are some challenges. I'm not, who's right, who's wrong here, I'm not sure. I'm highly suspect of not capturing much drought signal in MODIS NPP here. And that's largely because you've got this coarse nature of the MODIS cells, and the land cover's not changing. That would be one inclination. But you can see what we estimate in terms of NPP versus MODIS. Both the declining trend, a lot more variability in our estimates. Just if you're not familiar with what's been going on in California, this is just a quick time series of the precip anomaly from 2010 to 2015. Again, widespread drought in 2013 just impacting virtually all of the state. I think rainfall was down in like the 10 to 15% of normal type of range in 2013, and even here it was sustaining for many years. Okay, so this is what the projected now looks like. So looking out to 2100, this is total ecosystem carbon, and then this is how this total ecosystem carbon is partitioned into DOM, live, and soil pools here. And then this is our, referred to as net ecosystem carbon balance, and that's the annual source sink. So you see the variability in the historic period. Again, I talked about that. I think it was a source of 90 to a sink of 60. When you take the average of 32 models, you really kind of remove it, but the background, the 95% confidence interval is really picking up that historic range for the most part. the dark green area is kind of, this is what 50% of the models are saying the range might be. So what's driving all that uncertainty? And you know, this is something that's kind of being confirmed in several papers now. But if we just calculate the mean, so the gray shaded area here is that full 95% confidence interval. But the colored bars are the means based on the land use scenarios, the radiative forcing scenarios, and the climate models. You can see what's driving the spread there. It really is your climate model uncertainty. The climate models were designed, I mean, they're in one sense, right, they're designed to do this. They were purposefully selected to represent, you know, an average of, again, 32 models, hot, wet conditions, hot, dry conditions, and what they call a complement. So kind of in one sense, right, we're maximizing this variability through this selection of these climate models. But you can see the difference. And this really is driven by, for the most part, precip. And our model of NPP is based on this NC's empirical model, and it's precip limited. So in times where you don't have precip, NPP suffers, and that's what's driving our estimate. You can see precip being highly variable in here, but the models do kind of cluster up here versus down here. So the green and red, we're talking about the Hadley models and the Myrock models, and then the average and the hot wet are up here with a lot more precip. Temperature-wise, we're talking about, you know, an RCP 4.5 an increase of about 3C, whereas under RCA 5 we're approaching almost I think it's 6C in California. It'd be pretty hot. Hard to see, but this is NPP across all 4 climate models, and then so these are averages for all the climate models and land use scenarios, and then the colors are the RCPs, and this is NPP up top. This is heterotrophic respiration here. This is NEP, so and NPP minus RH. This is our land use land cover change losses, and then ultimately our NECB. And one of the things that we thought was neat, this model right here, Hadley, again, mentioned a minute ago, like in part it was selected because it has this period of exceptional drought. This is about a 20-year period where precip is lower than I think 80% of normal in the model. And they pulled that out for a reason in the assessment to examine the future of it.
NECB,
carbon balance. So it's the annual net biome productivity. Okay, and so if we just try to look at the differences in scenarios now, and this was kind of one of our main findings. This space, this shaded area here represents where California ecosystems would become a net sink and sequester more carbon than they would lose. And you can see virtually all the models sit in this space over here with the exception of 2 of them. And generally what happens is when you're at RCP 8.5 and then you go to RCP 4.5 for a given scenario, you increase carbon sequestration. That doesn't surprise most people. That's somewhat expected, right? Moving from here to here, for example. Okay? But it's not always the case. And this is, I think, a really important result of the paper, that there are situations where in some climate models, for whatever reason internal in the guts of that climate model, climate, at least with respect to carbon balance, gets quote unquote worse. And that's particularly the case under the average model, CAN-ESM, where we go the other way, right? We're here and we move this way. Here we move this way. And you know, the story there, it's not unsurprising, I guess. California is a really small place within the global model that's run, and you can have these weird dynamics going on, especially in a Mediterranean ecosystem like California. It's kind of not surprising, but it should, I think, be stated really clear that simply reducing global emissions and doing nothing else may make it hard for a place like California to meet certain climate goals that they have, because ecosystems are responding in an unanticipated way. On the flip side, so that's what this plot is showing here. On the flip side, when you reduce land use, going say from a high to a low land use future, you achieve a pretty reliably consistent benefit, right? So you're almost always increasing carbon storage or reducing net carbon losses. Okay, so the sensitivity analysis on CO2. I kind of talked about the motivation for this. We looked at various face experiments. Generally, face experiments show an increase of, 5, 8, 9 to 25, maybe even higher % increase when you bump up CO2. And typically that's been an increase of CO2 of about 50%, okay? So you increase CO2 by 50% and you're getting this mixed response by vegetation. This increases in NPP. And so what we do is we turn this response, the measured response from face experiments, into beta values. So that's the % increase in NPP for a 100 ppm increase in CO2. And that's what we did. We ended up calculating betas ranging from 2 to 14%. And then of course in our base scenarios it's 0. We imposed this on the CANI-SM, so our average climate model, and the BAU land use scenario. And we did it for both RCP scenarios. We also added one additional set of scenarios where we capped the CFE at 600 parts per million. Since that was kind of the upper limit of all the face experiments, RCP 8.5 CO2 hits 960, I think, by 2100. Well, you'll see what happens when you just let that run unabated, kind of unreasonable. And so ultimately, NPP gets calculated in the model as the base rate from our DGDM, going all the way back to IBIS. IBIS gives us an estimate for every ecoregion and state class of what NPP is. And we modify that on a pixel by pixel basis from PRISM climate normals. We further modify that in space and time, so ecoregions, time steps, and scenarios using our empirical NPP model. And then now we're adding in the CFE element. Okay. And this is what it looks like. So the gray are the scenarios I was just showing you, and you can see the uncertainty around them. And if under RCP 4.5, for example, if you just look at total ecosystem carbon storage, this is the range you get, spanning all of those CFEs that we introduce. You can see the uncertainty by doing that is just, it's massive. And this is what happens at RCP 8.5. So keep in mind we've got two scenarios. The green is just letting the CFE go all the way to 2100, and the orange salmon color is when you cap it at 600 parts per million. And this just plots CFE against net emissions and carbon balance. So these are our 32 future scenarios down here with no CFE. And you can see under RCP 4.5, just a moderate CFE effect turns the state from source to sink. And under RCP 8.5, even the limited one, right, the lowest CFE gets you about carbon neutral. So this is a really important parameter in the model that absolutely needs more attention. I mean, this isn't new. The folks working around this science know this and recognize it, but for people like me that try to model it, it's really important. And just to emphasize that, so this is RCP 4.5 and 8.5. This is our estimates compared with the raw NPP coming out of the CANI-SM Earth system model. Okay, so CANI-SM for let's look at RCP 8.5 is right here. And this is our base estimate with no CFE. Right, and so you look at those, and obviously the magnitudes are different. You're only talking about, there's about 15 grid cells that make up California in this Earth system model. So I think that's what's driving the magnitude differences. But if you're looking at the slopes, you get this huge increase in NPP under CANI-SM. And when we introduce our highest CFE, we're roughly able to mimic that trend increase. This is kind of going back to a CFE effect of about 28% coming out of the FACE experiment. So Norby's first papers on this were showing that, but subsequent papers showed that that may not persist. And they even urged caution to modelers continuing to use those high rates, and I think this supports it also. Okay, so conclusions. We project California ecosystems will continue to be a net source. The historical rate of 13.5 million metric tons, we don't project that severe of a decline. In fact, our average is sitting around half of that, like less than half of that. But we have a lot of uncertainty, again, from a source to a sink. Again, really driven by climate models. Wildfire and drought become pretty big drivers. Reducing global emissions doesn't always achieve benefits at local and regional scales, at least in terms of ecosystem carbon balance. Reducing land use is a pretty reliable way of getting some benefits back. And then CO2 is pretty important. Okay, so just quickly, we did all of that, that's just come out, but we also began using this same basic model to analyze the effect of climate management. Or ecosystem-based kind of carbon solutions. This was published by a group called Next 10. I'll share the slides. You can go to the link if you want. But basically, we looked at a set of 80 different policy interventions, and they were really focused around reducing fire severity and post-fire restoration, changing in forest management, some other restoration activities here in woodlands and riparian zones. A couple of agricultural ones, and then avoiding conversion. And so we ran these again in the model. We also had an economic component to this. Some folks down at UCSB jumped in and looked at the economics of the interventions themselves. Really neat work. USGS is not an author on this because of its heavy policy slant. But really cool work that's being turned into a journal paper right now. So this is going to be coming back. We're getting ready to do some reruns here. But again, kind of a neat story, right? Avoiding the conversion of these natural ecosystems often yields really strong positive benefits to the carbon. The one that we spent quite a bit of time on, and I think we're really getting pulled in to do more, is the reduction in fire severity. And so what we were doing was, in the model was, thinning treatment followed by a prescribed burn. And the question was, if you do that, you remove a bunch of carbon from the system, but do you get it back through avoiding high severity fire? The answer to that is no, you don't get it back, but probably the biggest reason is we didn't assume any prior knowledge of where the fires are going to occur. And a policy like this, you have to think of this in space and time. You might impose this policy, but if you shoot your policy here and all the fire occurs here, you're not achieving a lot. And so we're getting set to rerun the model with a series of experiments where we assume that our understanding of fire and where it's going to occur improves dramatically, and see if that helps reduce this barrier here. But it's a really exciting one. It's one that the state's really interested in us doing more work on. We're scaling this to national. So there's a lot of things that go along with doing that. I mentioned the age, but we've also got some really neat new data, county scale population projections under various shared socioeconomic pathways. The cropland data layers annual time series now. There's a lot of really good spatially explicit mapping for forest change. I urge caution. Be careful when you use some of it. And be careful how you interpret it, right? The whole use versus cover thing is really important. We're also expanding our forest classification. I mean, I'm talking to a bunch of folks that probably live and breathe forest. And I showed a model with one forest class. You guys are probably laughing at me. I have reasons for that, We're expanding it to be in sync with FIA forest groups. We're fully coupling our fire model, so there will be feedbacks between ex-urban development and fire emissions. There's also a whole new set of intervention scenarios. There's also a product being developed by USGS called LC Map. You'll be hearing more about it. I won't get into the details of it, but it'll be the way land cover mapping proceeds into the future. We're also kind of tweaking our carbon model to be a little bit more in line with Werner Kurtz's CBM approach, at least in terms of the pools and the fluxes that go along with it. Inclusion of lateral fluxes, which will be a pretty exciting one, including deposition into coastal wetlands, and then a harvested wood products sub-model to go along with it. And that's all I've got. Any questions?
Wait, any questions?
Must be one. No, you're not. My son.
I have one question.
Sure.
I'm curious how reasonable you think those carbon fertilization effects are. You mentioned a little bit about it. I mean, you didn't need much of a fertilization effect to go to neutral. Do you think that's reasonable?
I don't know. That's the honest answer. I don't know. It's not my area of science for sure. I think it's probably very dependent on ecosystem, ecoregion, forest type. I mean, I certainly struggle with the idea that we can double NPP purely based on pumping more CO2 into the atmosphere. I gotta think that there's a nitrogen limitation, a water limitation that ultimately is gonna cap that. But my cheap answer is I don't know. It's certainly as we're showing, a vitally important model parameter. We've got to get a better handle on it. I should say, in terms of sensitivity analysis, it's just one example. There's a lot in the model, and we've gotten a lot of push to really expand our use of that kind of a framework for things like background mortality rates, aquatic fluxes, things like that. Yeah.
I think you said at the beginning that the state tasked you with this project, is that correct?
Yeah, the land use, started with the land use scenarios to inform the fire model.
Okay, I know there's probably a ton of different answers to this question, but I was wondering if you could give just an example of how they might take all of these model results and put them to use.
Yeah, good question. So are you kind of more talking about in the policy context?
Sure.
So,
Or
This-
management?
Yeah.
Yeah,
How
so-
they might use it.
yeah, so from a policy context, what the state has a greenhouse gas reduction target that they've established, but it's entirely been set for all those other sectors, transportation. They've intentionally avoided ecosystems because they don't know. And I think as we've been working with them, it's kind of become clear that you have to consider ecosystems. If your goal as a state or a county or whatever is to reduce the contribution to atmospheric CO2 by X or by some number, but at the same time, you're not accounting for this, what could be 10%, you're missing it. And so I think that would be the first thing, is that work like this will be used to establish a baseline for ecosystems. That's what's needed. And then when they begin to test various policy interventions, how does it bend against some baseline? So I think that'll probably be the first one. We just received funding from the California Utilities grant, and it's a big collaborative effort across, tons of universities, various government agencies, and what they want is a deeper dive into land use fire, the interactions, improve our fire model. They want improved fire modeling, they want updated scenarios. So I think that's kind of one of the things coming out of this is just the recognition that we're just touching the surface right now with our understanding. We recognize ecosystems are important, we need to dive deeper. In terms of real management, are they gonna take the maps, for example, and go do something with them? I don't know. I struggle with, what do we do with these maps, right? I mean, we have 3,200 times 100 years worth of maps. I'm not even sure what to do with the maps at this point. We haven't gotten to the point where we're looking, say, at spatial pattern, and then going in and saying, well, if we want to maximize, so we've talked about reducing land use, right? But we haven't talked about it in the context of pattern. I'm sure there's a ton of work there that could be done to take the maps that have come out and begin layering in new assumptions about what should be protected, or rewind, what could be protected in order to continue to maximize carbon benefits. We just haven't gotten there.
So you showed the overall carbon budget, and the variability from year to year seemed to be much more from ecosystems than from the other sectors.
By far.
And then you showed and then 2 slides later, you show the variability in NPP in your model versus MODIS. And I wondered if you had the MODIS NPP driving the overall assessment in the previous graph, if your variability would be way down.
Absolutely.
So the amount of variability...
Really driven by our assumption about NPP. Absolutely. The year-to-year variability, if we stuck MODIS, if you look at the time series of MODIS in California, it varies by plus or minus 5, maybe 10% per year. And it's not very much at all. And so, that would absolutely
Change that picture.
It would definitely smoothen it out. The NPP side, this is probably our biggest, it's certainly the most important parameter driving the results right now. At least driving the variability of the results.
Yeah, you showed that the uncertainty is driven largely by the climate models.
Yes.
Across the different scenarios.
That's right.
But for the historical case, the variability, it seems to be driven by NPP.
Yeah, so the interannual variability is definitely NPP driven, but by the NPP submodel. But the climate models do this. Now they're still bouncing, right?
But so for this sort of calibration exercise here, are we getting the history?
Right.
I worry about that.
Worry about
the difference between MODIS and this.
Well,
and given the importance of that black line.
So that's the key is what does this represent? And I'm very skeptical. Again, it is a model, right? And so I'm always leery about relying too heavily on it as gospel. And it's just, and the big thing is if you actually look at the spatial NPP data, the area where all the tree mortality was, for example, doesn't change. Does not change at all. It's still forest, and even though its whole stands are brown and dead, it's still a functioning forest in terms of MODIS NPP. I've looked at it up here as well, especially kind of out going towards the coast, south of the Olympics, and the same kind of thing. All that harvest that's going on barely budges NPP. We know that a 2-year-old regenerating forest has a very, very different NPP than a full mature forest. So I worry about this. And I will say that the NC's model that we used was really well, and it's a build on from a model, the Miami model. And it was based on plot level data. Really well calibrated, but it's the annual variability, I agree. Now, again, it's the annual variability. If you start looking at the trends, this separation, this is what we're talking about in terms of the annual, but that is what
That's the climate.
the climate models are just going and completely different directions. Again, by design.
So this is almost like a party, but we're going to go and join a party.
Sweet.
So you're welcome to join us.
Awesome. Thanks, guys. Appreciate it.